All right, so as we start chapter 9, we start looking at testing a claim for proportions. Again, last chapter 8, we were doing inferencing about the population for confidence intervals for proportions. Now we're going to be doing some hypothesis testing for the proportions. So here we have an example. A basketball player claims to make 80% of his free throws he attempts. You've seen him play basketball before and you don't believe him. You ask him to shoot some free throws. Suppose he shoots 50 free throws and makes 32 of them. Is his claim true? But he just had a bad streak today. So is it true that he is an 80% free throw shooter, or hey, did he just have a bad streak, or hey, his claim is false? That's what we're going to try to look at and do a hypothesis to test about. So in this problem, what is the sample proportion? Well, our p hat here, our p hat would be he made 32 out of 50 free throws, which is 64%. So 6.64. What can we conclude about the player's claim on the sample data? Well, here's one thing we say. We say when you are a 50 or 80% free throw shooter, you don't always make 80% of your free throws. Instead, we average all performances of shooting free throws to get that 80%. Sometimes you may shoot 7 out of 10, sometimes you may shoot 9 out of 10, or you may hit 8 out of 10 when you go to the free throw line. But as a collective whole, it came out to be 80%. So how do we determine the likelihood or probability that he had a bad streak? We can perform a simulation to find out. So in this case, we used the Fathom software to simulate 400 sets of 50 shots, assuming that the player really is an 80% free throw shooter, to try to get all the random samples of what could come about. The dot plot of the results is shown. Each dot is a proportion of shots made for each group of 50 attempts. And so as we look over there, we have all these 400 shots, all these different 400 samples of them doing 50 shots. There's times when he did hit 80% a bunch, and then there's times when he hit 90%. There's some times when he got above 90%. There's also times over here where he did below. We did circle where his sample proportion p hat is, and so we're going to talk about that. It asks us, in how many of the 400 sets of shots were at our sample proportion of 0.64 or lower? Well, technically, at our 0.64, there was one example of it, and then two more. So there's a total of 3. Okay, so there's a total of 3 out of the 400 samples in the simulation were at ours or below, which works out to be about 0.0075. Now, you can say how strong the evidence the player's claim is by giving the probability that he will make as few as 32 out of 50 free throws if he really makes it in a long run. Now, what is the probability that he made only 32 shots out of his 50 tries just by chance, so he had a bad streak? Well, based on this simulation, our estimate of this probability is 0.0075. That's our observed statistic of p hat equal to 0.64. Again, the observed statistic of p hat being 0.64 is so unlikely. Again, 0.0075 or 0.75% is so unlikely. That gives that gives us convincing evidence that the player's claim is not true. So it's so unlikely for that to happen that his claim is not true. That we believe that he is not an 80% free throw shooter. So things you want to think about is be sure that you understand why this evidence is convincing. There are 2 possible explanations. The fact that our virtual player made only 64% of his free throw shooters. The player claim is correct. That's the one thing we consider, where p is equal to 0.8, where it's 80%, and by bad luck, which is a very unlikely outcome, occurred. And it does happen sometimes when you think about just real life of guys will go into a basketball game in the college or in the pros, and they say they're a 85 or a 90% free throw shooter, and then they miss the first or five free throws that they take, and they have a bad streak. And it's just one of those unlucky things that happens in the circumstances. The second thing to consider is the population proportion is actually less than, meaning his percentage of it is less than. So the sample result is not an unlikely outcome. So, maybe he was just inflating the number to make it sound good. And maybe he's actually a 70% free throw shooter. And we could go through and run the whole process again to say, okay, if he told us that, is it likely that he is? So a significance test is a formal procedure for comparing observed data with a claim, which is our hypothesis, with a claim, and that's known as our hypothesis. Again, with a claim whose truth we want to assess. We express the results of a significant test in terms of a probability that measures how well the data and the claim agrees. Now, in our significance test, first, we deal with claims about the population, is what they deal with. Claims about the population. We ask if a sample data gives good evidence against the claim. If we took many random samples and the claims were true, we would get a result like this some percent of the time. Our basic idea and outcome that would really happen if a claim were true is good evidence that the claim is not true. Now, as we look at stating our hypotheses, we have to do this at the very beginning of as we approach the problem. Our null hypothesis, noted by H sub 0, so H naught is usually how it's pronounced, is a statement of no difference. Again, depending on the courses that you take in statistics, based on some of what I've done, this publisher in the AP kind of goes with this. The null hypothesis is going to be, we're always going to say that whatever it is, it's either, for our null hypothesis, it's either mu is equal to 0 or p is equal to 0. Or no, I wouldn't say 0, just equals. Let me back that up. Let me get rid of that equals. Boom, boom. We're going to use the equal sign. There's no difference between the two. And hence why we see this one right here. So since we're dealing with proportions, we see... here's our notation for our null hypothesis, is what we're going to end up using. When we get into stuff in the next couple chapters with means, we'll just have the mu in that place there. We use the parameter symbol is what we got to use in our hypothesis statements. We don't use the statistics symbols in that process. Alternative hypothesis is the H sub A, or ha, as I'll refer to it. The claim that we hope or suspect is true. We suspect that is true instead of the null hypothesis. You have several types of tests. You have a one-sided test, and there's two versions of it, and you have a two-sided test. A one-sided test is an alternative hypothesis which claims that the actual parameter is less than or greater than the null hypothesis. It will always be in the form of our p is greater than some number, or our ha is less than some number. Again, the numbers that are in both places, whether in our null hypothesis and our alternative hypothesis, those got to be all the same numbers. It's the same number used in both places, and it's always the population number that we use. We never use the p hat, the sample statistic, in our hypothesis statements. Just a little note there. Two-sided hypothesis test will claim that the ha as the actual parameter is not the parameter. So it's stated so we will use the not equal to symbol for a two-sided. And as we look at reading word problems, sometimes they'll give us the good indicator, hey, that it's less than this, or it decreased something, or hey, it improved test scores, or something's greater than. So we know it's one-sided which way, using which symbol. If they don't specify some type of language like that in the problem, then we just go ahead and do a not equal to. I'll go ahead and assume that there's no difference is what we end up doing. So here's an example. Mike is an avid golfer who would like to improve his play. A friend suggests getting new clubs and lets Mike try out a 7-iron. Based on years of experience, Mike has established that the mean distance that the ball travels when hit of his old 7-iron is 175 with a standard deviation of 15. He is hoping that his new clubs will make his shots with the 7-iron more consistent, therefore a less spread is what he's hoping. He wants less spread. That's the key thing here that helps us write our hypothesis statements. So he goes to the driving range and hits 50 shots with the new 7-iron. So all they want us to do here is just set up the hypotheses. So for our null hypothesis, our H sub O, we're going to say that P is equal to, okay, what was the standard deviation? 15 yards. Again, we use the population value here, population parameter, their value for the null hypothesis. And we use it again for the alternative hypothesis. So now they said less spread. So the ha would be P is less than 15 yards. Okay. And then now we'll go on to another example. Again, you can always pause, try this next one, then see if you did it right. It says Vitamin, a brand new brand of vitamin, claims the radio spot that people who take vitamins wake refreshed and ready for the new day within 5 minutes of their alarm sounding. Vitamin's internal research department conducted a test to support the claim heard on the radio. So with this in mind, let's highlight a couple of things here. It claims that this people 5 minutes. So again, that's not really a proportion. That's really an average. Okay, the average of 5 minutes. So that lets me know that my null hypothesis, we're going to be using the mu symbol. So we're going to use mu is equal to 5 minutes. And now, when we look at the alternative hypothesis, they say within 5 minutes. So that means that less than 5 minutes. So 5 minutes was the average, but within the 5 minutes. So we're saying anywhere from 1 to 2 to 3 minutes. So so that ends up being our null and our alternative hypothesis. So again, a one-sided test here. All right, next example. The school principal is not pleased with this first semester exam scores of the two first period U.S. history classes. The mean test score for both, again, mean test score. So that lets me know, mean test score lets me know that I'm dealing with mu. Mu is 72. He believes the student's final exam score average will increase because the two teachers will teach the second semester by combining the classes and using a team teaching approach. All right, fantastic. So what's our null hypothesis? Again, we want to put the H sub O to indicate to the grader what we're doing. So mu is equal to 72. And then our ha, we know we got to use the mu. They said he believes it's going to increase. So that means we're going to be greater than 72. Again, different statistics courses, when you look at going to college, some of them will actually let you write like a greater than or equal to in the alternative hypothesis. This course steers towards you're always doing an equal sign in the null hypothesis, and then the alternative hypothesis is always going to be an inequality. And it's either the less than, the greater than, or the not equal to. Those are the only three options. Next example, heading into an election, Jack needs 50% of the vote. To win the election, Jack is feeling confident that he will win the election. Is his confidence warranted? All right, well, let's see. So what is the ho? P is equal to 2.5. It's 50%. And then we have the or higher. So that would mean the alternative hypothesis, P is greater than 0.50. The alternative hypothesis should express the hopes or suspicions we have before. Key thing here, before we see the data. It is cheating to look at the data first and then frame the hypothesis to fit the data that's shown. So, I've talked about it in previous classes. I have an assumption about how many kids actually do their homework honestly, or as opposed to using like AI to get through their homework assignments. And so, I think there's probably about 55 to 60% of the high school students in a math class use AI to get their homework done. That is what I think is my percentage, my population proportion. And so if I was doing a hypothesis test and gathering data from the school, that's my first. I'm going to go ahead and set that down as my null hypothesis that p is equal to 0.5. I actually think it's or 0.55. It's actually greater than that. I think it's more than that. So my alternative hypothesis would be that it is greater than 0.55. Our hypotheses always refer to a population, not to a sample. Again, we do not want to use the sample data in our hypothesis statements. We only want to use the population information. If unsure, we use a two-sided. So this is what I was talking about before. If they don't specify, or if we're not sure, if we're doing a greater than or less than, then we just do a not equal to. Is it different from what we're saying for the population parameter? So if sometimes they say that is it different from 50% or is it different from 75%? So that would indicate that, hey, they think it's this exact amount. Is it different from it? And so we do either side would be fine. And that also lets us know, like a one-sided test, when you think about a normal curve for probabilities, is meaning we're shading one side of the test. We're either doing a less, if it's a less than, we're doing a left tail shade. If we're doing a greater than for the alternative hypothesis, then we're doing a right tail, so shading on the right side of the normal curve somewhere. Whereas if it's a two-tail, then that means it's almost like it's basically we have tails on both sides, and the open space in the middle is blank. So we're shading two outside portions, is what we're doing. Again, you're going to see me use some of that technique with shading on graphs as we do some stuff in the future sections. The probability the interpreting the p-value, it's the probability that measures the strength of evidence. Against the null hypothesis, and this thing is called our p-value. The smaller the p-value, the stronger the evidence against the null hypothesis. Again, the smaller the p-value, the stronger the evidence against the null hypothesis. The p-value is the conditional probability, so it's the probability that of the alternative hypothesis given the null hypothesis has already occurred. That's what it's referring to. Given that the null hypothesis has already occurred, what's the probability of the alternative hypothesis occurring? That's what it basically is. Again, smaller the p-value, the stronger the evidence against the null hypothesis. So that's a key thing to remember as we do analyze our p-values and we interpret things. Significance level. To determine the p-value is considered small. In this case, to determine what p-value is considered small, which would reject our null hypothesis, our H sub O, or if it's large, and when we see a p-value that's large, we would fail to reject the null hypothesis. We compare it to a significance level, which is known as alpha. Significance. And that's this little symbol here. That's alpha. That's the Greek letter alpha. Okay, so I usually draw it more like the fishy symbol. Significance level requires evidence against the null hypothesis to be so strong that would happen less than alpha percent of the time. And again, there's three main alpha percentages that we use, and we'll talk about them again here in a little bit. They're usually it's a 1% alpha, it's to 5% alpha, or a 10% alpha. Those are the three that we gravitate towards. using, and that they'll end up using. When our p-value is less than, when it is less than our chosen alpha, we say that the results is statistically significant. Again, put a star next to that one. When we are less than, when the p-value is less than the alpha, we say the results are statistically significant. Significant doesn't mean important. It just means not likely to happen by chance. And this is where they ask the little sidebar questions of, hey, is it statistically significant? And then that's where we could come up with the little statements of saying that, hey, that this lets us know that, it's likely, it's not to happen likely by chance. If you are going to draw a conclusion based on statistical significance, the significance level should be determined always before. You always want to, just like we're setting up the alternative and a null hypothesis in advance before we do stuff, we want to set the significance level, saying, hey, we're going to do this at a 5% significance level, 10%, or a 1%. Significant levels should range from basically 0.1 to 0.001. Again, that would basically be 10% down all the way to about 0.1%. But usually, again, in our course, we're doing from 10% to 1%. And the most common here, and the reason why is, as we're getting ready to talk about, courts will accept a 5% or lower for the significance level. So when in doubt, if they don't tell you which one to use, then we're going to automatically use a 0.05%. What we're going to do, we're going to do a 0.05 alpha or a 5% alpha. And again, we got to state that as we write up a process. We're going to actually state what that amount is. All right, statistical significance. The final step in performing significance test is to draw a conclusion about the completing claims you were testing. We will make one of two conclusions. One of two conclusions based on the strength of the evidence. The first one is that we reject the null hypothesis. We reject the null hypothesis. When do we do that? We do that when the p-value is less than our alpha, whatever the alpha percentage is. So when we get our p-value as a percentage when we're done with the process, if it's less than the alpha percentage that's stated in advance, then we get to say we reject the null hypothesis. The other option we have is we fail to reject. We fail to reject the null hypothesis. When does that occur? That's when the p-value is greater than the alpha value. This does not guarantee that the null hypothesis is true. Just because we fail to reject doesn't mean that it's true. It's just that there is not enough evidence to reject it. And then a key thing here, we don't use in this course accept the null hypothesis. Okay, if you say we accept the null or referring anything to the alternative hypothesis, like say, hey, we accept the alternative hypothesis or reject the alternative hypothesis, you'll lose credit on the AP exam. So your two choices for after we get the data and we get the information back is either to reject the null hypothesis or fail to reject. We have some scripts that we'll practice doing, and again, stay along with those scripts to make sure we stay pretty consistent. So in the free throw shooter example, the estimated p-value was 0.007. That is strong evidence, because we think about no matter which we use, if we're comparing it to 0.1 or 0.05 or 0.01, which is typical, all those alpha values we are way lower than. So that is strong evidence. We have strong evidence to support the claim that, hey, he is not an 80% free throw shooter. So for that reason, we would reject, and if we did the whole situation, we would reject the null hypothesis. If we did the full test out and did it in a process, we would say we would reject the null hypothesis. And then that's basically meaning, hey, in favor of the alternative hypothesis. That is actually less than 80%. He's actually a less than 80% free throw shooter. Now, here's our example. When Mike was testing again the 7-iron, the hypotheses we had written earlier were as follows, where the standard deviation is the distance of Mike's golf balls using his old 7-iron. So based on 50 shots with the new standard new 7-iron, the standard deviation was, and again that's the S sub x is equal to 10.9 yards. Great. A significant test using the sample data produced. So they went through the process we're going to learn, and they found that the p-value was 0.002. So they asked us, one, to interpret it in context, and then they ask us to compare it with a significance level and decide, okay, what would we do? So here's the interpretation we would say about the p-value. If the true standard deviation is 15 yards, the probability of getting a standard deviation of 10.9 yards from our sample is 0.002. Now they ask us to go through and then decide, okay, will we reject the null hypothesis, or would we fail to reject the null hypothesis? And so typically we start these things with saying, since 0.002 is less than 0.01, we reject, again, it's less than, so we reject the H sub O, the null hypothesis. We have convincing evidence. We have convincing evidence to support the claim that the new standard deviation is less than 15 with the new 7-iron. All right, next one. So for the second semester projects in AP Stats, Zenon decided to investigate if students at his school prefers name brand potato chips to generic potato chips. He randomly selected 50 students and had each student try both types of chips in random order. Overall, 34 of the 50 students preferred the name brand potato chips. Zenon performed a significant test using these hypotheses. Again, population, 50%. They either, half of them would like it and half of them would not. And then he thinks that it is, so they said they prefer name brand chips, so that it's actually greater than 50% is what he's thinking. So that's why we have that greater than symbol there. Where P is equal to the true proportion of students at the school that prefer name brand chips. They did the process that we'll get to work on eventually. And then the resulting p-value was 0.0055. Now, what conclusions can we make at each of the following significance level, and then state the conclusion in context? So first off, for part A, what can we conclude at an alpha of 0.01, which is also alpha is equal to 1%? All right, because we see it in both formats. Usually they go ahead and move the decimal force. Otherwise, we got to say 1% means 0.01. So since 0.0055 is less than 0.01, we reject the H sub O. Okay. Now we could go in there that it is we have convincing evidence to support the claim, blah blah blah. On the next one, we would say since 0.0055, and I'm going to put down the 0.001. And as I look at that, well, technically 0.0055 is bigger than 0.001, so it's greater than. So in this case, we would fail to reject. We fail to reject the H sub O. On the first one, we have convincing evidence. We have convincing evidence to support our claim. On the second one, we do not. We do not have convincing evidence. I do not have convincing evidence to support the claim. So again, if you're saying fail, then we should say we do not have convincing evidence. If we say we reject, then we have convincing evidence to support the claim. All right, now, I think one of I've always felt this little part right here is the more confusing piece. And I have an extra video I found a couple of other professors have put out about, is it a type 1 error, is it a type 2 error, as we get ready to talk about this. Again, these are typically multiple choice questions. And then we get the little sidebar question on a free responses like, hey, what would be a type 1 error in this instance? And, what's the impact of what that type 1 error is? So I have a couple resources I'm going to post on Google Classroom for you all to look at. And they do a really good job of explaining the difference between the two. And then sometimes setting it to a real world scenario in the standpoint of like if somebody's being tried for murder and they are convicted, but they're actually innocent. And then the other option for a type error, the errors would be, hey, they are set free, but they're actually guilty. And so as we look at those consequences of a type 1 and a type 2 error, I would definitely recommend you watch that. So when we draw conclusions about a significance test, we hope our conclusions will be correct. That's what we're hoping. And then, so now before we fill out the table, let's do something down here at the bottom. What happens when our conclusions are wrong? What happens that our conclusions are wrong? We made the wrong decision. There are two types of mistakes that we can make. A type 1 error, and what is a type 1 error? That's when we reject the null hypothesis when it is true. All right, when it is true. This is one of those kind of like 1 in a million cases. So as we look at in the court of law, we determine that somebody is guilty when they are actually innocent. Okay. Now, what is a type 2 error? We fail to reject the null hypothesis when it is true. And this would be the case of we determine they are innocent when they are really guilty. So when we look at the table up above, and this is where the other videos I think do a good job of explaining this more than I can. This is where we reject the null hypothesis when the null is true. Then we made the wrong decision, and that's why this is what we call the type 1 error. And they actually use Roman numerals on these ones for the type 1 and type 2. And then if we reject the null hypothesis and the null hypothesis false, which means the alternative was true, basically, we made the right decision. Okay. If the whole null hypothesis was true and we failed to reject the null hypothesis, hey, we made the right decision. And then here, if the null hypothesis is false and we fail to reject the null hypothesis, we made the wrong decision here, if that's what we came up with, and this would be an example of a type 2 error. All right, so again, watch those extra videos I put on there, and that should help with those because they do a good job explaining with it. Our next example, heading into the election, Jack needs 50% of the vote to win the election. Jack is feeling pretty confident that he will win the election. Is his confidence warranted? So here's our null hypothesis, that it's 50% and that he feels confident he's going to win it, so it's greater than 50%. Well, they ask us to describe what is a type 1 error and its consequence in this setting here, and then what a type 2 is. Again, this is a typical thing they'll ask on an AP test, or in a free response, or in a multiple choice, free response or the other, for you to be able to pick what would be the example of it. So here's what the type 1 error is and its consequence. We determine that Jack has the votes. So he's got the majority of the votes. When he doesn't. Now, what's the consequence about this? Well, he thinks he's going to win, but doesn't. Now, what is a type 2 error? We determine that Jack does not have the votes when he really does. Now, what's the consequence here? Spends more money. He spends more money trying to drum up support, trying to get the votes when he doesn't need to. Now, just thinking about the election we just had back here in 2024, and it's not a matter of which candidate won or not, it's just in the general part. I just remember looking at the different news broadcasts on different stations, and leading up to the election and even after the election, there was a lot of polls that were done by different organizations that were saying that the Democratic Party was actually in favor. Presidential candidate Harris was in line to win the election, even all the way up through that day and until the votes started coming in that evening. And then with that in mind, they all thought that she was going to be president. But when it came all down to it, those polls were not correct. They ended up, they did not lead to the outcome they talked about. And so they were pretty confident she was going to win. That may have changed her course of action of where she was visiting, where they were putting extra money towards stuff, as all the polls through October were kind of showing she's in the lead. And that may have changed their strategy. And then she ended up losing the election. And so that there's the consequence of some of those polls led to the wrong interpretation, and they may have decided, we don't need to travel to some of these other states, and unfortunately it may have backfired on them. So that's some of the consequences, and I just think about that being in the real life part of something that happened recently, towards our class in this topic. So error probabilities. So what are some error probabilities? We can assess the performance of a significance test by looking at the probabilities of making these two errors. So the probability of making a type 1 error is basically your alpha percentage. The probability of a type 1 error is whatever your alpha is. So if your alpha is a 5%, there's a 5% chance of making a type 1 error. And that means you're wrong, and so forth. What is the probability that as we look at the right side, here, it's basically 1 minus, and that's 1 minus beta, okay? And then now, what is our conclude, when we look at as we look at these, and we'll talk about alpha and beta more in class a little bit, very, there's small amount on the test, on the AP test about this. So we'll talk about it more in class and give you a couple clear examples of doing it. All right, coming up on the next slide. Why is power important? And again, they mentioned the power up here in our little examples here, the power of the probability. So we're going to talk about that a little bit more. So the probability of making a type 2 error is 1 minus the power. 1 minus the power. So the higher the power, the lower the chance of making a type 2 error. Low power means that null hypothesis is unlikely to be rejected and the experiment will be inconclusive. And basically, what does that mean? We did all that work for nothing. Unfortunately, calculating the power of a test can only be calculated if you know the true population value, which again, we very rarely know, okay? So here is an example of just going through, calculating the power, the p-values, and going through, what are the power. And so we'll talk about this a little bit more in class, and then because this gets more into the heart of actually doing the test and going through the process. This section mainly deals with the interpretation and how would you write the stuff as opposed to the actual test. Now, what does the power mean? Interpreting the power. Again, in this previous problem, there's a 75.17% chance of correctly rejecting the null hypothesis when the true proportion is 11%. Again, they found the power by doing a normal CDF and going through the process here. So again, we'll practice that in class. There's not too many examples of it, so I'll pull a few together to kind of put them in your notes when we get in there. How is power affected by different parts of a study? Remember, we talked about before on how we can, in the confidence interval, how can we make the interval less narrow or maybe make it wider by adjusting some things, maybe the confidence level or adjusting the size of our sample. So to get a higher power, we would want to increase the alpha or increase the significance level. So go from a 1% to a 5%, go to a 10%. We could increase the sample size. We could decrease the standard deviation, therefore making it not as spread apart. We could also increase the difference between the null value and the true population value. And then we use a one-sided test. Those are all the ways we can increase power. And these are typically, those things right there are usually good multiple choice questions ones for the AP test where they say, hey, how can we increase the power of this test? And we look for these options as options to be able to choose from. How could we get a lower power? We basically do some of the opposite stuff here. We decrease a significance. We decrease the alpha. We decrease the sample size. We increase the variance, the spread, the standard deviation. We decrease the difference between the null hypothesis and the true population value. Or we use a two-sided test. So we use like a not equal to, where it's different, okay? All right, next part, almost done. So we got a couple examples just to run through, and or an example to run through and then it's a little bit of notes and we're done. The manager of a fast food restaurant wants to reduce the proportion of drive-through customers who have to wait more than 2 minutes to receive their food once their order is placed. Based on store records, the proportion of customers who had to wait at least 2 minutes was 63%. To reduce the proportion, the manager assigns an additional employee to assist the drive-through orders. During the next few months, the manager will collect a random sample of drive-through times and test the following hypotheses. So he wants to decrease from 63%, where P is the true proportion of drive-through customers who have to wait more than 2 minutes for their orders to be placed. Suppose that the manager of the fast food restaurant wants to change some aspect of the study. How will these changes affect the power of the test? Well, to reduce the possibility of a type 1 error and avoid the possibility of unnecessary paying an extra employee, the manager reduces the significance level from 10% to 1%. So in this case, again, our type 1 error, to reduce the type 1 error, which means when we do that, we're lowering, we're lowering our alpha. Okay, we lower our alpha. So our alpha went from, our alpha went from 10% to 1%. Now, what did that do? That lowered our power. When we decreased the significance level, that lowered our power, is what that did. Again, going back to the previous thing here, if we decrease the alpha, we lower the power. The other option the manager did was to justify the additional cost of the extra employee. The manager decides that the true proportion must be reduced to 53%. So again, he reduced the true proportion. He reduced the P, which was 0.63, down to 0.53. So he reduced the population proportion. So by doing that, by dropping taking the P down, take the initial P down from 63 to 53. What happened was, looking at our chart here, if you that would be an indicator of that increasing the difference. So he actually raised the power. Raised the power. To get faster results, the manager reduces the sample size from 250 to 100. So again, decreasing sample and decrease and decreased. So if we go back up to our chart here, if I decrease the sample, decreasing the sample tells me that I lower the power. So I lower the power. All right, next one here, significance level. If you insist on a smaller significance level, such as 1% rather than 5%, you have to take a larger sample. A smaller significance level requires stronger evidence to reject the null hypothesis. The practical importance at any significance level and desired power, detecting a small difference requires a higher power. Requires a, I got my looking off my stuff wrong here. Requires a larger sample than detecting a large difference. If you assist on higher power, such as a 99% rather than 90%, you will need to take a large sample. Higher power gives a better chance of detecting a difference when it is really there. All right, so that's the end for the day. And again, make sure you watch those extra videos that I put out there on the type 1 and type 2 error, just to kind of clear that up a little bit. and give you a little bit extra information on that one. Again, make sure you take a look at the section. They give some good tips in our section in the book as well.